You have three switches in a room. One of them is for a bulb in next room. You cannot see whether the bulb is on or off until you enter the room. What is the minimum number of times you need to go into the room to determine which switch corresponds to the bulb in next room? So to simplify, there are three switches in a room where one of them is assigned for a bulb in the next room. You can't see whether the bulb is on or off until you leave the room. Find the minimum number of times you have to go into the room to identify which switch corresponds to the bulb in the other room. Let me explain the solution now. The answer to this puzzle is 1. You need to enter the room only once to determine which switch corresponds to the bulb. Let me explain the solution in detail. First, switch on the first switch and wait for some time, say 5 minutes. Now switch off the first switch and switch on the second switch. Now enter the room. If you find the light bulb glowing, then the second switch corresponds to the bulb. If the light bulb does not glow, just touch the light bulb to check if it emits heat. If the bulb exhibits at least some heat, then the first switch corresponds to that bulb. If the bulb does not exhibit heat, then the third switch corresponds to the bulb. Let me repeat the solution now. You need to enter the room only once. First, you switch on the first switch and wait for some times, say some 5 to 10 minutes. Now switch off the first switch and switch on the second switch. Enter the room. If you find the light bulb glowing, then the second switch corresponds to the bulb. If the light bulb does not glow, just touch the light bulb to check if it emits heat. If the bulb exhibits at least some heat, then the first switch corresponds to that bulb. If the bulb does not exhibit heat, then the third switch corresponds to the bulb. You are given 8 identical looking balls. One of them is heavier than the rest of the 7. All the others weigh exactly the same. You are provided with a simple mechanical balance and you are restricted to only 2 uses. Can you find the heavier ball? Let me repeat the puzzle. You are given 8 identical looking balls. One of them is heavier than the rest of the 7. All the others weigh exactly the same. You are provided with a simple mechanical balance and you are restricted to only 2 uses. Can you find the heavier ball by using only 2 uses of the mechanical balance? Let me explain the solution now. For convenience sake, let's name the balls 1 to 8. First, we weigh 1, 2, 3 on the left and 4, 5, 6 on the right. This is the first measurement. There are 3 scenarios which can arise from this. Let's consider the scenario 1. If the left side is heavier, then we know that one of 1, 2 or 3 is the heavier ball. Now in the second measurement, weigh 1 on the left and 2 on the right. We will know if 1 or 2 is heavier. If they balance out, then 3 is the heavier one. Thus, heavier ball is identified by exactly 2 measurements in this scenario. Let's consider the scenario 2. If the right side is heavier, then we know that either 4, 5 or 6 is the heavier ball. Now in the second measurement, weigh 4 on the left and 5 on the right. By doing this, we will know if 4 or 5 is heavier. If they balance out, then 6 is the heavier one. Thus, heavier ball is identified by exactly 2 measurements in the scenario 2. Let's consider the final scenario, that is scenario 3. If 1, 2, 3 and 4, 5, 6 balance out, then we know either 7 or 8 is the heavier one. Weigh both of them to find out which one is heavier. Again here, heavier ball is identified by exactly two measurements. Let me summarize. The first step is determining which set of three balls contains the heavier one. So choose balls 1, 2, 3 and balls 4, 5, 6 and weigh them. If one set is heavier, save those three balls. Pick two balls and place for measurement. By doing this, we will know which one is heavier. If they balance out, then other is the heavier one. If neither side is heavier in the first step, proceed with balls 7 and 8. In the final weighing, weigh both of them to find out which one is heavier. By following these simple steps, we can find which ball is heavier in just two measurements.
The scenario comprises of a wobbly bridge and four people. It is the night time and the people have only one torch. Without torch, one may risk his life in crossing the bridge. Also, we have a condition. The bridge is not quite strong and can hold only two persons together at once. The four people take different time to cross the bridge. The timings are 1 minute, 2 minutes, 7 minutes and 10 minutes. Since the torch is a necessity and the bridge can't hold more than two persons at a time, two persons must travel at a time, out of which one must return with the torch so they don't risk their life crossing in the dark. What is the shortest time that will be required for all of them to cross the bridge? Let me simplify the puzzle. Four people need to cross a bridge at night. Unfortunately, they have only one torch and the bridge is too dangerous to cross without one. The bridge is only strong enough to support two people at a time. Not all people take the same time to cross the bridge. Times for each person is 1 minute, 2 minutes, 7 minutes and 10 minutes. For example, if the two people with the speed 7 and 10 minutes were to cross together, it would take 10 minutes, leaving 17 minutes for one of them to return and get the rest moving. Can you find what is the shortest time needed for all four of them to cross the bridge? Were you thinking of using the fastest person who takes 1 minute to travel to and fro till everyone has reached the other end? Yes, that can be done, but it will take 10 plus 1 plus 7 plus 1 plus 2 equals 21 minutes in total. If you pay attention towards finding a way to merge the one taking 7 minutes and the one taking 10 minutes, we will have to acknowledge the fact that one of them will also have to return back, which will take much more time than 21 minutes. What if we use the person taking 2 minutes to escort the one taking 1 minute across? Let's come to the conclusion. So in first step, 192 crosses the bridge and 2 returns with the torch. Here time taken is 2 plus 2 equals 4. In the second step, 7 and 10 crosses the bridge and one who was already in the other side come back. Here time taken is 10 plus 1 equals 11. In the final step, 1 and 2 crosses the bridge. Here time taken is 2 minutes. In such a manner, the total time taken will be 2 plus 2 plus 10 plus 1 plus 2 equals 17 minutes. Alternatively, the same time can be achieved like this. 1 and 2 go first, then 1 comes back, then 7 and 10 goes and 2 comes back, then 1 and 2 go again. It makes a total of 17 minutes. You are a king of an empire. You have a servant working in your palace. He works all the 7 days and you only pay him in the form of gold bar. You must pay the worker for his work every day at the end of the day. If you are only able to make 2 breaks in the gold bar, how will you pay the servant if the servant works for the equal time every day and thus equal amount must be paid at the end of the day? If you are thinking of how to cut in such a way that you are able to make 7 equal pieces, you are thinking in the wrong direction. You should give more stress on how to make the transactions with the worker. So the trick is not to try and how to cut in such a way to make 7 equal pieces, but rather to make transactions with the worker. Make 2 cuts on the gold bar such that you have the following sizes of bars. Bar A should be 1/7 of the bar, bar B should be 2/7 of the bar C should be 4/7 of the bar. Let's check whether it is going to work. When the day 1 ends, give bar A to the worker. Here you remain with bar B and bar C. Worker possess bar A. When the day 2 ends, give bar B to the worker and take the bar A back. Here you remain with bar A and bar C. Worker possess bar B. When the day 3 ends, give bar A to the worker. You remain with bar C. Worker possess bar A and bar B. When the day 4 ends, give bar C to the worker and take back bar A and bar B. Here you remain with bar A and bar B. Worker possess bar C. When the day 5 ends, give bar A to the worker. You remain with bar B. Worker possess bar A and bar C. When the day 6 ends, give bar B to the worker and take back bar A. Here you remain with bar A. Worker possess bar B and bar C. When the day 7 ends, give bar A to the worker. Here you remain with no bar. Worker possess bar A, bar B and bar C. Thus by the end of 7 days, you have taken care of everything.
A farmer lives on a small plot of land next to a river. One day he travels across the river in a small boat and purchases a fox, a chicken, and a bag of corn from a feed and supply store. When the farmer returns to his boat to cross the river again and go home, he realizes he has a problem. The farmer can only take one item in his small boat at a time, otherwise he risks capsizing. He cannot leave the fox alone with the chicken because the fox will eat the chicken. He cannot leave the chicken alone with the corn because the chicken will eat the corn. How does farmer will cross the river without losing anything? A farmer lives on a small plot of land next to a river. One day he travels across the river in a small boat and purchases a fox, a chicken, and a bag of corn from a feed and supply store. When the farmer returns to his boat to cross the river again and go home, he realizes he has a problem. The farmer can only take one item in his small boat at a time, otherwise he risks capsizing. He cannot leave the fox alone with the chicken because the fox will eat the chicken. He cannot leave the chicken alone with the corn because the chicken will eat the corn. How does farmer will cross the river without losing anything? First, the farmer must take the chicken across the river, leaving the fox and corn alone together on the starting side. This is a good move because fox will not eat corn. Then the farmer goes back and gets the fox. When he takes the fox across the river to the other side, instead of leaving the fox alone with the chicken, he swaps them out and takes the chicken back to the starting side. In the starting side, he then swaps the chicken out for the corn and brings it across, leaving the fox and corn alone on the far side. Finally, he goes back to get the chicken, bringing all three items across the river to the far side without letting anything eat anything else. By following this simple logical approach, farmer brought all three across river without losing anyone. You have three jars that are all mislabeled. One jar contains candies, another contains sweets, and the third jar contains a mixture of both candies and sweets mixed in random proportions. You can put your hand in a jar and pick only one eatable at a time. Tell the minimum number of eatables that have to be picked in order to label the jars correctly. Assume that the shape of the candies and sweets are identical and there is no way to differentiate them by touching alone. Let me explain the solution now. When I first saw this puzzle, I have spent more time to find the solution. Even though puzzle looks very simple once you know the solution, but it's really confusing puzzle. Logic lies in first selecting the correct jar in finding the solution. Let me explain the solution step by step. In step 1, you have to pick only one eatable from jar C. Suppose the eatable is a candy, then the jar C contains candies only because all the jars were mislabeled. So remember, this jar cannot contain sweets because it is mislabeled. The only choice on this jar is candies. Most importantly, this is enough to label other two jars correctly. Let me explain how. Now, since the jar C has candies only, jar B can contain sweets or mixture. But jar B can contain only the mixture because its label reads sweets, which is wrong. Therefore, jar A must contain sweets. Thus, the correct labels are jar A contains sweets, jar B contains candies and sweets, jar C contains candies. Thus, answer is just one pick of an eatable is required to correctly label the jars. There are many variations to this puzzle, but logic remains same. Let me share one more variation. This problem is also called jelly beans problem. This is also commonly asked interview puzzle. You have three jars that are all mislabeled. One jar contains apple, another contains oranges, and the third jar contains a mixture of both apple and oranges. You are allowed to pick as many fruits as you want from each jar to fix the labels on the jars. What is the minimum number of fruits that you have to pick and from which jars to correctly label them? This puzzle also requires the similar logic which I have explained earlier. So let me explain the solution. Let's take a scenario. Suppose you pick from jar labeled as apple and oranges. You got apple from it. That means that jar should be apple as it is incorrectly labeled. So it has to be apple jar. Now the jar labeled oranges has to be mixed as it cannot be the oranges jar as they are wrongly labeled, and the jar labeled apple has to be oranges. Similar scenario applies if it's a oranges taken out from the jar labeled as apple and oranges. So you need to pick just one fruit from the jar labeled as apple and oranges to correctly label the jars. Thus the answer is just one pick of a fruit is required to correctly label the jars.
In this visual brain teaser, you can see three glasses on the left that are full and three on the right that are empty. You can only move one glass to make a row of alternately full and empty glasses. Which one do you move? This is an interesting brain teaser, requires out of box thinking. Let me explain the solution now. For convenience sake, let's name the glasses A, B, C, D, E, F. A, B, C, D, E, F are 6 glasses. A, B, C are full and D, E, F are empty. They are placed in a row. The important point here is in the brain teaser, it is mentioned that you can only move one glass. But there are no rules mentioned on the restrictions on operations that can be performed on that glass. So what we can do is we have to move the full glass B and to pour total juice or water of it from glass B to the glass E. Then put the empty glass B in its own position. After performing this activity, B glass is empty and E glass is full. Now the row will be like this. A is full, B is empty, C is full, D is empty, E is full, F is empty. Thus, by moving only one glass, we can make a row of alternately full and empty glasses.
Think that you have two identical ropes, which are non-uniform in composition. Each rope takes 60 minutes to burn, but the ropes are not identical, meaning 90% of the rope may burn in 5 minutes and rest 10% may take 55 minutes or any such composition. You don't have any watch but a lighter. How will you calculate 45 minutes? So I will repeat the puzzle. You have two identical ropes which are non-uniform in composition and each rope takes 60 minutes to burn. But their composition is non-uniform, meaning 90% of the rope may burn in 5 minutes and rest 10% may take 55 minutes, or 80% of the rope may burn in 5 minutes and rest then may take 55 minutes, or any such composition. You don't have any watch but a lighter. So the question is, how will you calculate 45 minutes? As it is told in the question, the ropes are non-uniform. It means that if you cut a rope in two half, then both half may not take 30 minutes each to burn. But on a whole, the rope will take 60 minutes to burn. This approach is not going to help. So in order to calculate 30 minutes, you only need one rope. So what you can do is burn the rope from both ends. It will take the rope 30 minutes to burn completely. Even though it is non-uniform, but if you burn on both the sides, it's definitely going to take 30 minutes because the composition does not matter since you are not burning the rope from one side. So in order to calculate 45 minutes, the one rope is not sufficient. You need two ropes. Let's call the ropes A and B and follow the below process in order to measure 45 minutes. What you have to do first is burn rope A from both ends and rope B from one end. So rope A will completely burn in 30 minutes. So because it is put on fire from both the ends. As we saw in the question itself, the rope takes 60 minutes to burn. Since you are burning on both the sides, the whole rope will burn in 60 minutes. So when rope A is burnt completely, you have already measured 30 minutes. But the rope B would have burnt for 30 minutes. It does not mean that the rope B is off burnt, but it has already taken 30 minutes and the remaining portion of the rope will burn in another 30 minutes. So at this point, lit the other end of rope B as well. It will take another 15 minutes for rope B to burn completely. So that's how you are going to measure 45 minutes. So I will repeat the solution. So what you are supposed to do is first burn rope A from both ends and rope B from one end. So rope A will completely burn in 30 minutes because it is put on fire from both ends. When rope A is burnt completely, rope B would have burnt for 30 minutes. So it does not mean that rope B is off burnt. At this point, lit the other end of rope B as well. It will take another 15 minutes for rope B to burn completely. So that's how you have measured 45 minutes.
There is a square grid comprising 25 dots. A circle is attached to the grid. What is the largest number of dots the circle can pass through? Let me explain the solution now. Here is how we can solve this problem. The diagram shows a circle that goes through 8 dots. There are other circles that also go through 8 dots, but this is the largest number of these dots that a circle can go through. Hence 8 is the largest number of dots the circle can pass through, 2 each on the top, bottom, left and right sides for a total of 8. You have a torch that takes 2 working batteries.
You have 8 batteries, but only 4 of them work. What is the fewest number of pairs you need to test to guarantee you can get the torch on? So let me repeat the problem. You have a torch that takes 2 working batteries. You have 8 batteries, but only 4 of them work. What is the fewest number of pairs you need to test to guarantee you can get the torch on? Let's check the solution. Let's call the batteries as B1, B2, B3, B4, B5, B6, B7 and B8. Torch will work when both the batteries are working. It will not work if any of the battery is faulty. With the best case, if we take 2 pairs of batteries and put them in slot 1 and slot 2, test them out. If working, then fine. Else take another 2 and test them out and continue doing so till you get the correct pair. If you are lucky in these 4 turns, torch will work. But let's say we were most unlucky and it did not work all the 4 times. Also, the whole objective is to find the solution for worst case scenario and not for the best case. Now let's group the batteries in 2 groups of 4. There can be these cases in group of 4. If all 4 batteries are working, then take any pair and we will get working battery in just one chance. If only 3 batteries are working, we will get working batteries in max 2 picks. If only 2 batteries are working, scenario becomes tricky because this will open up multiple possibilities and end up in more iteration to find the pair to switch on torch. If only 1 battery is working in the group, then scenario becomes more complex. Hence, grouping batteries in 2 groups with 4 batteries each is not the correct approach. Now I will explain the most efficient way of finding the solution for this puzzle. We know that out of the 8 batteries, only 4 are in working condition. We need 2 good batteries to run. Let's try to divide the 8 batteries in a group of 3, where group 1 and group 2 contains 3 batteries and group 3 contains 2 batteries. By grouping the batteries like this, we are making sure that at least one of the group has 2 working batteries. This is because there are 4 working batteries and only 3 groups present. Going through logic, there must be at least 2 working batteries in any of the groups. Also, by grouping like this, we are reducing the number of combinations required to find the working pair for the battery. So this is the logic for this particular puzzle. So now let's find how many combinations are possible for each group. Let's go one by one. In group 1, which consisting of B1, B2, B3, possible combinations are B1, B2, B2, B3 or B1, B3. Hence total combinations in group 1 is 3. In group 2, B4, B5, B6, possible combinations are B4, B5, B5, B6 or B4, B6. Again, in this particular group, the total combinations possible is 3. Finally, in group 3, B7, B8, possible combinations is only 1. So the total combinations in group 3 is 1. We know that at least one of the groups has 2 working batteries. By logic, any one of these combinations must work. So adding all the combinations in all 3 groups, it will yield 7. Hence, most number of trials needed is 7. So let's summarize. Break the batteries into 3 groups with 2 groups of 3 batteries and 1 group of 2 batteries. By doing this, you are guaranteed that one of the groups has 2 working batteries. Both of the groups of 3 have 3 possible combinations of 2 batteries and the group of 2 only has 1 combination. So 3 plus 3 plus 1, which equals to 7, tries at most to find 2 working batteries.
You have 10 boxes that contains balls with each of the ball weighing 10 grams precisely. Now among the boxes, one of the box comprises of defective balls with each defective ball weighing 9 grams. You have been provided with an electronic weighing machine, but you are allowed to use it only once. Can you find the box with the defective balls? The puzzle looks difficult, but by the time you understand the solution, you will find that it was way easy than you were thinking. For convenience sake, let's name the boxes from 1 to 10. In order to solve this problem, you have to leverage the fact that you know exactly what each good ball is supposed to weigh and what each defective ball is supposed to weigh. Many of us instinctively will take one ball out of each box and try to find a way to make it work, but the trick is to take different number of balls from each box. The number of balls you pick from each bag is equal to the box number. For example, pick one ball from box 1, two balls from box 2, three balls from box 3, and so on, and finally 10 balls from box 10. In total, you will have 55 balls. If all of the boxes have good balls, then the total weight of these balls would be 1 plus 2 plus 3 plus till plus 10 times 10, which is equal to 550 grams. This is because each ball weighs 10 grams. 550 grams is not possible because we are already told in the puzzle description one of the box comprises of defective balls with each defective ball weighing 9 grams. So this is the catch to solve this puzzle. If box 1 has defective balls, then the total weight should be 1 gram less than expected. It is because only one ball weighing 9 grams. If box 2 has defective balls, then the total weight should be 2 grams less than expected. It is because 2 balls weighing 9 grams. Similarly, if box 3 has defective balls, then the total weight should be 3 grams less than expected. It is because 3 balls weighing 9 grams. So once you weigh the set of chosen balls, find out the difference between the total weight and the expected weight. That number represents the box number which contains the defective balls. By following these simple steps, we can solve this puzzle and defective box can be identified with single weigh. We have to divide a square into 5 parts such that 4 parts among them are equal. The condition is that even once the pen does not get up. In simple words, solution to this puzzle must be achieved without lifting pen. Let me explain the solution now. We can solve this puzzle like this. We have to draw an inscribed circle within the square. In this way, all corners of the square are equal and square will be divided into 5 parts. The interesting part of the puzzle is even if we draw a circle inside square, then we do not need to lift the pen. As we can see here, square is divided into 5 parts: part 1, part 2, part 3, part 4, part 5. And part 1, part 2, part 3, part 4 are equal. Thus, by drawing inscribed circle within square, we can divide a square into 5 parts such that 4 parts among them are equal. This is one such question frequently asked in interview. Do prepare for this.
We are given a series of numbers which contains integers from 1 to 50, including both 1 and 50. However, the numbers are in a jumbled form, that is, they are not arranged in increasing or decreasing order, and there is one integer missing. You have to identify the missing integer logically. Let me explain the solution now. As per the puzzle, there are series of numbers which are given and it contains integers from 1 to 50 and which includes both 1 and 50. However, the numbers are in a jumbled form and there is one integer missing. Our task is to identify the missing integer logically. Okay, we know that the sum of all the numbers from 1 to n can be calculated by using the formula n times n plus 1 over 2, where n is the last number in the series. Remember, this formula is applicable for only positive natural numbers. Let's understand this equation with simple example. Let's consider a series with 5 numbers 1, 2, 3, 4, 5. We can use the equation to find the sum of these numbers. Here the last number in the series is 5, hence n is 5. Hence this will result in 5 times 5 plus 1 over 2, which is equal to 15. Similarly, we will try for 50 numbers and hence n becomes 50. Therefore, sum of all the numbers from 1 to 50 is 50 times 50 plus 1 over 2. Here n is 50. And after simplifying, and we get 50 times 51 over 2. And further simplification, we get the value 1275. Hence, sum of all numbers from 1 to 50 is 1275. Therefore, all we need to do is to sum all the integer present in the given series and subtract the sum from 1 to 75. The difference between 1 to 75 and this sum would give us the missing integer, because 1275 is the sum of natural numbers from 1 to 50, and this number is sum of natural numbers from 1 to 50 without including missing number. Hence, subtracting the sum of given series from 1275 will fetch the missing number.
There are 8 pills. They are all of the same size and color. One pill weighs slightly more and is poisonous. You have a balanced scale and can only use it twice. How can you find the poisonous pill? Let me explain the solution now. First of all, split the pills into the following groups. So group 1 must contain pill number 1, 2, 3. Group 2 must contain 4, 5, 6. And group 3 must contain 7 and 8. For your first weighing, put 3 pills on one side, 3 on the other, leaving 2 set aside. If one side is heavier, the poisonous pill is in that group, but if they are the same, it's in the 2 set aside. If the weight balances, then group 3 contains the poisonous pill. If they are different, the heavier group contains the poisonous pill. For the second weighing, pick the group the poison pill is in. Put 1 pill on each side and 1 off to the side, unless it was in the group of 2 from before, in which case don't set any aside. If the scale says a side is heavier, that's the side that's got the poison. If you picked a 3 pill group and the scales are the same, then the one you didn't weigh out of that group is the poison. So to simplify, if the poison pill in group 3 balance 7 against 8, the heavier one is the poisonous pill. If the poison pill in group 2 balance one of the pills against another in the same group, if they are the same, then the poisonous pill is the one not weighed. If they are different, the heavier one is the poisonous pill. Only 2 balances required to find the poisonous pill.
There are 3 keys that open locks of 3 different gates. In how many attempts you can figure out the key for each gate? Let me explain the solution now. There are 2 interpretations to this puzzle. First interpretation is to identify the key for each gate and opening it. Other one is just to identify the key associated with the gate. According to first interpretation, that is to identify the key for each gate and opening it. Assuming that it is always the last key that works, the first lock will take 3 attempts. having eliminated one lock per key. The next takes 2 attempts, leaving 1 attempt for the last lock. Hence 3 plus 2 plus 1, which is equal to 6. Hence, to match all the keys to all the locks, the maximum number of tries is 6. The minimum is 3. The formula is 3 factorial, or 3 times 2 times 1, or 6. The first lock takes at most 3 tries. The second lock 2 tries, as one key was eliminated. The last lock takes 1 try, as only 1 key is left. Hence, the best performance in 3 attempts for 3 gates, getting right in the first attempts for all of the 3 gates, and for the worst performance in 6 attempts for 3 gates, getting right in the third attempt for the first gate, getting right in the second attempt for the second gate, and getting right in the first attempt for the third gate. Let's solve the problem for second interpretation, that is, just to identify the key associated with the gate. Let us take one lock at a time. Now for one lock, we have 3 keys, but if 2 keys does not open it, it becomes obvious that third will do so. So maximum attempt for lock 1 is 2. Similarly, we have 2 keys now for the second lock, but if one does not work, we know that other would do so. Hence, maximum attempt for lock 2 is 1. And for lock 3, we do not need any attempt because there is only one key left, which would be the right key. So maximum attempts in this particular interpretation will be 3. Hence, for the first interpretation, that is to identify the key for each gate and opening it, the answer is 6. And for the second interpretation, that is just to identify the key associated with the gate, the answer is 3. You are on your way to visit your grandma, who lives at the end of the valley. It's her anniversary and you want to give her the cakes you have made. Between your house and her house, you have to cross 5 bridges, and as it goes in the land of make-believe, there is a troll under every bridge. Each troll quite rightly insists that you pay a troll toll. Before you can cross their bridge, you have to give them half of the cakes you are carrying, but as they are kind trolls, they each give you back a single cake. How many cakes do you have to leave home with to make sure that you arrive at grandma's with exactly 2 cakes? Let me repeat the puzzle. You are on your way to visit your grandma, who lives at the end of the valley. It's her anniversary and you want to give her the cakes you have made. Between your house and her house, you have to cross 5 bridges, and as it goes in the land of make-believe, there is a troll under every bridge. Before you can cross their bridge, you have to give them half of the cakes you are carrying, but as they are kind trolls, they each give you back a single cake. How many cakes do you have to leave home with to make sure that you arrive at grandma's with exactly 2 cakes? Answer to this puzzle is 2 cakes. At each toll bridge, you are required to give half of your cakes and you receive 1 back, which leaves you with 2 cakes after every bridge. Let's analyze the solution. In the first toll, you give 1 cake to troll because we are assuming that you started journey with 2 cakes, and in each toll, you have to give half of the cakes. In this case, it is 1. In return, you receive 1 cake back, hence there is no loss to you. You started with 2 cakes. After first toll, you still having 2 cakes, and this will repeat in all remaining tolls. So if you start with 2 cakes, you will end up with 2 cakes after the last toll. Thus, answer to this puzzle is 2. This is a very simple scenario. What if the question is asked in such a way that there are only 3 bridges, and how many cakes do you have to leave home with to make sure that you arrive at grandma's with exactly 3 cakes? This requires generalized solution. Let's assume you are carrying X cakes. Since you have to give half of the cakes you are carrying and each give you back a single cake, the number of cakes after first bridge is x divided by 2 plus 1, and after solving this equation becomes x plus 2 divided by 2. After second bridge, number of cakes left is x plus 2 divided by 2 whole divided by 2 plus 1. After solving this equation becomes x plus 6 divided by 4. So after third bridge, number of cakes left is x plus 6 divided by 4, which is actually the total number of cakes remaining after the second toll, divided by 2 plus 1. After solving, equation becomes x plus 14 divided by 8. And we know that the number of cakes left after third bridge is 3. Solve this equation for 3. After solving, we get the x value is equal to 10. So thus, if there are only 3 bridges and number of cakes you have to leave home with to make sure that you arrive at grandma's with exactly 3 cakes is 10 cakes. This is generalized solution. You can use this technique for any number of cakes. One person has some money in his pocket. He visits 4 churches on the way. As soon as he visits any church, the money in his pocket gets doubled, and on his way out, he donates $100 to each church. In total, he visits 4 churches. After visiting the last church, his pocket is empty of all the money. So how much money he had initially? Let me simplify the puzzle. One person has some money in his pocket. He visits 4 churches on the way. As soon as he enters a church, his money gets doubled and he offers $100 in each church. Thus, his pocket gets empty after he returns from the 4th church. Now the question is, how much money he had initially? Let me explain the solution now. Let's assume a person began his quest with X dollars. In first church, as soon as he enters the church, his money is doubled to 2x. On his way out, he donates $100, therefore he is left with 2x minus $100. In second church, as soon as he enters the church, his money is doubled to 2 into 2x minus 100. 2x minus 100 is the money left before visiting the second church. On his way out, he donates another $100 and he is left out with 4x minus $300. In third church, as soon as he enters the church, his money is doubled to 2 into 4x minus 300. 4x minus 300 is the money left before visiting the third church. On his way out, he donates another $100 and he is left with 8x minus $700. And at fourth church, as soon as he enters the church, his money is doubled to 2 into 8x minus 700. And we know that 8x minus 700 is the money left before visiting the fourth church. On his way out, he donates another $100 and he is left with 16x minus $1,500. And according to the question, after his last visit, he completely runs out of money. According to our equations, at the end of the fourth church, so the equation is 16x minus 1500. Therefore, 16x minus 1500 is equal to 0. After solving for x, we get x equals 93.75. Hence, a person had started his quest with $93.75 in his pocket.
John has 3 cakes. One cake is poisoned and he knows which one. What yes no question can you ask John to find out which cake is poisoned? Let me explain the solution now. This particular puzzle can have multiple interpretations. Let me explain the solution which I think is the best solution. Let's make a couple of assumptions to answer this puzzle. The first one is that we are allowed to cut the cake, and second one is that John says the truth only among the 2 options, yes or no. So we have 3 pieces of cakes, say A, B, C. Let us cut the cake C into 2 equal portions, say C1 and C2.
Now put C1 with A and C2 with B. So we have now two segments of cake pieces, that is AC1 and BC2. Now our question to John is, John, is AC1 more poisonous than BC2? If John says yes, that means A is poisoned, throw it out and eat B, C1 and C2. A is poisonous because A is larger in size compared to C1. If John says no, that means two options. First option is AC1 is less poisonous or BC2 is more poisonous. Second option is AC1 and BC2 are equally poisonous. Here it is clear that A is not poisonous. In this case, I suggest we better don't go for any adventures, eat the piece A, leaving B and C for John. In any case, he can't eat both. He would eat only the pure cake and would definitely throw away the poisonous one. Again, here there is no clear guarantee that poisonous cake is identified, but at least this will provide us the logical conclusion. Let me explain another interesting interpretation. According to this interpretation, one question is sufficient to finding a single non-poisonous cake, but one question is insufficient to determine the poisonous cake. Let's A, B and C be a labeling of the cakes. If you only have option to ask one question and can take no other action, there is no such question. A yes/no question gives you one bit of information. You need two bits of information to distinguish the poisonous cake from the non-poisonous cakes. As I have already mentioned, one question is sufficient to finding a single non-poisonous cake. Let the cakes be labeled A, B and C as I have already mentioned. You can then ask the question, is the poisonous cake either A or B? If the answer is yes, then we know that the cake C is non-poisonous. If the answer is no, then you know both cakes A and B are non-poisonous. Note that this question is insufficient to determine the poison cake. If the answer to the question is yes, then all you know is that either A or B is poisonous, but not which one. You would need an additional question to determine that. So there is no single correct answer which can be a solution to this riddle. Do share your answer in the comment section. But what's important in interviews is the interpretation that you are presenting to the person who is asking you the question. If you give a broader picture how you interpreted this particular question, I think that should be sufficient for anybody to choose you for the company. John and Peter are selling chocolates. John was selling at the rate of 2 pieces per rupee and Peter was selling at the rate of 3 pieces per rupee. Now both of them decided that they will mix their chocolates and sell them at the rate of 5 pieces for 2 rupees. After selling whole chocolates, they found that the total collection is rupees 7 less than what they would get by selling them separately. Note, initially both have equal number of chocolates. Find how many chocolates each of them had initially. Let me explain the solution step by step. Let us assume that John and Peter had X number of chocolates, each of them initially. Money earned by John when he sells chocolates separately is total chocolates with John over number of pieces per rupee. Hence, money earned by John is X over 2 as he sells 2 chocolates per rupee. Money earned by Peter when he sells chocolates separately is total chocolates with Peter over number of pieces per rupee. Money earned by Peter is X over 3 as he sells 3 chocolates per rupee. Total money earned by both of them by selling chocolates separately would be X over 2 plus X over 3. Now let us find out the equation for money earned if they sell chocolates together at 5 pieces per 2 rupees. We know each have X number of chocolates, so the total number of chocolates that both have is 2 times X. They sell 5 chocolates per 2 rupees, and hence every 5 chocolates is considered as one piece sold for 2 rupees, which is 5 over 2. Hence total money earned in combined manner is total chocolates with John and Peter over 5 pieces per 2 rupees. It is given as 2 times X over 5 over 2. Now the equation becomes X over 2 plus X over 3 equals 2 times X over 5 over 2 plus 7, as there is 7 rupees short when they sell chocolates in combined way. Solving the above equation for X gives the number of chocolates each of them had initially, which is 210 chocolates. Hence answer to this puzzle is 210 chocolates. A horse and a camel were carrying boxes on their backs. The horse started complaining to the camel that his load is too heavy. The camel replied, "Why are you complaining? If you gave me one of your boxes, I would have double what you have. And if I give you one of my boxes, we too would have an even load. How many boxes do each of the animal, that is horse and camel, is carrying?" Let me explain the solution now. Let's assume C be the number of boxes that camel is carrying and H be that being carried by a horse. As per first part of camel's statement, that is, if you gave me one of your boxes, I would have double what you have. This can be expressed in the form of equation like this. C plus 1 equals 2 times H minus 1. C plus 1 because as per the statement, if you give me one of your boxes, which means we need to add 1 to number of boxes that camel is carrying. And 2 times of H minus 1 is because in the same statement it says adding one more boxes to C will result in double what horse have. We have to subtract 1 because this equation is valid if one box is given to camel. Now solve this equation. After simplification, equation becomes C plus 1 equals 2H minus 2 and C equals 2H minus 3, and call this as an equation 1. Now in second part of camel's statement suggests, if I give you one of my boxes, we too would have an even load. This can be represented as C minus 1 equals H plus 1 and C equals H plus 2. We know as per the first equation, C equals 2H minus 3. Now substitute the value of C here. Equation becomes 2H minus 3 equals H plus 2. After solving, H equals 5. Again putting the value of H in the equation 1, which gives C equals 2 times 5 minus 3, which is equal to 10 minus 3, and which is equal to 7. That is C equals 7. Thus answer to this puzzle is horse is carrying 5 boxes and the camel is carrying 7 boxes.